Third experiment in the syllabus of computer aided engineering for Pune University is plate shell element structural and structural linear and non-linear analysis. So we are going to conduct this experiment with the open source software Lisa 8.0. So I have divided this experiment with two examples. The first example is on structural linear analysis and the second example on non-linear analysis. So now first the experiment number 3. Okay. So this example we are going to solve for the linear analysis. As you can see in the figure, a bar of 10 inches length is there. The left end of the bar is fixed one. At the right end 1000 pound force is applied. The cross section of the bar is rectangular with width 2 inches and height 1 inch. So in Lisa software there is no provision for the units. So make sure that for all the variables you take the consistent units. So material properties in the numerical given as modulus Young's modulus E is equal to 30 into 10 raised to the power 6 psi. Poisson's ratio 0.3. So the moment of inertia, the formula for the rectangular section is bh cube upon 12, so which comes out to be 0.167 inch raised to the power 4. So now we will solve this example with the Lisa software. So I will begin with this tool new node. Click on this new node. Then so here I will create a 8 node shell element. So for that I will have to first create the 8 nodes. The first node I will create at 0 0 0. Add. The width of the section along the z-axis is 2 inches. So second node I will take at 1, add, then 2, add, then along y-axis total is 1. So first I will take 0.5, then 1, so now click on the close button. So now on the screen you can zoom into the screen with the help of middle mouse button. So as you can see, the total 8 nodes are created. 1 2 3 4 5 6 7 8. Now I will click on the new element. So click on this new element. So there are so many elements are provided in the library of this software. So you can select this quad 8 shell element. So total 8 nodes are required for this shell element. So here in this window you can type 1, 2, 3 up to 8. So node number from 1 to 8 separated by comma, add. So as you can see on the screen, element is created. So in the tree also you can see a default one element is created. So now after selecting this, so click on this face, select this entire face, then click on the extrude button. So the thickness along So minus x-axis, the length of the bar is 10 inches. So along minus x-axis 10 inches, and you want to create a solid bar. That's why number of divisions are 1. So okay. So again you can zoom out with the help of middle mouse button and reposition the geometry of the bar at the center of the screen with the help of right mouse button. So next step is to assign the material to this bar. Okay, so I will right click on this in the tree menu and select the assign material. So in the mechanical tab I will select this isotropic. The Young's modulus in the numerical is given as 30 into 10 raised to the power 6, and Poisson's ratio is given as 0.3. So I will click on close. So next is I will apply the boundary conditions, that is fixed support and the load. So click on this middle button, select faces, then with the help of a middle mouse button rotate this object and select the left hand face. Then in this tree menu right click on loads and constraints and click on the fixed support, new fixed support, create from current selection, okay. So now again to reposition the geometry you can click on this isometric view. So next you select this select nodes button, then select this top middle node, then in the tree menu right click loads and constraint, new force along y axis in the downward direction, so minus 1000 Newton. Okay. Now you can right click on the solution and solve. Okay. The solution is over. You can click on the displacement magnitude. Okay. So the displacement is 0.048. So the first example is linear structural analysis. So in this example both the geometry is linear and the material is linear. Also the constraints are also linear. So in order to see the von Mises stresses are, the maximum value is 1.45 into 10 raised to the power 4. So you can see the entire results in the table. Double click on this table, select all and update. So for each node total 8 nodes are there, total 20 nodes are there. So for 20 nodes you can see the displacement stress values. Okay. So now also you can click on this solution and click on the animate button to see the animations. So I will keep these default values over here and click on the play button. So here you can see the animation. So now here you can note down this von Mises stress. The stress value is, say for example 1.452 into 10 raised to the power 4 for 1000 Newton force. So what I will do in the force here, I will increase this force from 1000 to 2000. I will double the force and I will cross check the stress value. Okay, then again on the solution right click solve. So now click on the von Mises stresses. So you can see the 2.905 into 10 raised to the power 4, exactly the double value for the force of 2000 Newton in the downward direction. So there is a linear relationship between the applied force and the stress, and also you can check the displacement magnitude. The displacement magnitude is also double. So now The next example we are going to solve for the non-linear structural analysis. So now I will click on this new button, then again I will start with the same number of nodes. The first node at 0 0 0, so I will create the 8 nodes. So here the first we are supposed to create a non-linear geometry, so that is why I will take here 0.25 distance along z axis. Then next is 0.5, then along 0.125, then 0.25, now I will click on the close button. So as you can see in this example, the total 8 nodes are created: 1 2 3 4 5 6 7 8. So now I will click on this new element button. Again I will select the same element, chord 8 shell element, and I will enter here the node numbers from 1 to 8 separated by comma. So add. So you can see one element is created here, okay, on the screen. So with the help of this face tool, select faces, select this entire face and click on. So in the earlier example, the total length of the bar was given as 10 inches. So I will divide this 10 inches into 3 inches, 3 inches and 4 inches to create a non-linear geometry. Okay. So I will click on extrude and I will enter here along minus x-axis 3 value and number of subdivisions 1 to create a solid element. So you can zoom out and reposition this geometry at the center. So now you can click on this select faces tool and rotate the geometry with the help of middle mouse button and select the left hand face. Now right click on this face and select mesh tools, scale. I will scale this left hand face with the 1.5 factor along y axis and 1.5 factor along z axis. So I will click on OK. So now what I will do, I will extrude this up to 3. So along minus x axis 3 and 1. I will click on OK. So you can click on this isometric view. So again select this face tool, select faces, select this left end face and repeat the same procedure. So mesh tools, scale, here I will use the scale factor as 2 along y axis and scale factor along z axis 2. OK. Now I will extrude this face up to 4 inches. Click on the extrude here, 4. So OK. So now click on this isometric view button. So now total, as you can see, 3 elements are there, 1 2 3. So it's a non-linear geometry. Okay. The cross-sectional area of the first element is varying, the second element is also having varying cross-sectional area, and the third element is having the uniform cross sectional area, and the total length of the bar is 10 inches. So now I will right click on this in the tree menu and assign new material. So now we have applied the non-linear geometry. Now we will apply the non-linear material. So you can select this anisotropic 3D. So here the elasticity matrix will appear. So here you can enter the 21 different values for the Young's modulus. See, on the first row 6 values are there, on the second row 5 values. Okay, so here I will enter 30 into 10 raised to the power 6, comma 24 10 raised to the power 6, comma 28 10 raised to the power 6. Randomly I am selecting these values just to explain you the application of non-linear material. 27 into 10 raised to the power 6, so I will select these 5 values, and so on the second row you can see the 5 different values. On the third row 4 values are there. On the third row you can see the 3 Young's modulus values, and overall it is called as elasticity matrix. So you can click on close. So now the geometry is non-linear, and also we have entered the non-linear material properties. So now we will apply the loads and constraints. So we will fix this left end, and we will apply a 1000 Newton force at the middle node of the top face. So with the select this select faces button, then rotate with the help of middle mouse button and click on the left face. Now in the loads and constraint, right click new fixed support, create from current selection, OK. So again you can click on the isometric view. Now select nodes, select this middle node, then in the tree menu loads and constraints, right click and new force. So along y axis 1000, again in downward direction you can use minus sign, minus 1000. OK. So now you can click on the right click on the solution and solve. Okay. So here you can check the displacement magnitude, which is 2.95, and the von Mises stress value is 4.07 into 10 raised to the power 6. So again you can see the entire result in the tabular format by double clicking on the table, select all and update. So here you can see the displacement value and stress value for all the 44 nodes. Okay. So now you can click on the solution and animate. With the default values I will click on play button. So here you can see the animation. So now just note down this von Mises stress value, which is 4.073 into 10 raised to the power 6 for the 1000 Newton force. So now I will double click on this force and I will double this force from 1000 to 2000. So click on OK. Again right click this solution, solve. Now check the von Mises stresses. The value is 8.14 into 10 raised to the power 6, and the displacement magnitude is 5.902. So I hope that you have understood this experiment. Okay, thank you very much.